Thank you everyone for coming. And those of you all who are here physically and those joining remotely. We're going to talk about power analysis and choosing a sample size for a research study. If you're joining us remotely, I recommend that you mute your microphone and make sure it's muted. But if you have a question, please feel free to unmute and just ask away. And actually, that applies to everybody. If you have a question, interrupt me. That's fine. And better we address the question right away rather than, from that time on, you're distracted and or confused. And that'll be great. All right, so before I start with talking about power analysis, you know what? Actually, reminder to me and to everybody else to mute your phone. I think mine's muted, but I'm going to double check. I'm turning it off. All right. Okay. Everybody else do that too. Great. So we're going to talk about, I just wanted to say a couple words about our consulting office here, Smarter Consulting. Then kind of introduce the idea of power analysis, and then kind of go through the steps to conducting it in a really kind of conceptual sort of way with a couple of examples. And then I think that might be a good time for a very short break, followed by actually going through some power analyses using two programs that you can download for free from the internet if you saw the email, G-Power and PowerUp. And if you haven't downloaded them, I'll show you how. It's very, very simple. And then the last thing is I'll just say a couple words about doing a Monte Carlo simulation for power, which is a much more general way of doing things, but also takes a lot more work. And just so you know what it is. All right. So Smarter Consulting is our quantitative consulting office that we have here. It stands for Statistics, Measurement, and Research Design Techniques in Education Research. And you can thank Tasha Baretbas for that very clever acronym. Although whenever I introduce myself as the Smarter Consultant, I feel very conceited. But I don't mean it literally. So I'm the director, Adam Sales. Youngri Lee is our GRA. She's great. And if you are here, I think that's the next thing. So we have a website you can go to. You can navigate there from the College of Education website, here, and then you go to research, and then research support, and then Smarter Consulting. Or this is a shortcut URL to get there. This is my email address. So we have consulting meetings. Anyone who, if you have any sort of question about anything, but we probably will only be able to answer things about quantitative methods. Any questions, then sign up for a meeting. I consult with staff and faculty, and Youngri consults with grad students. If you're applying to a grant, definitely get in touch with us, and we'll write the method section. We'll help with the power analysis, although, after today, y'all will be experts in that. And we will help with any sort of data analysis. If you already have a grant and you realize you need some help with it, we can sign up for a contract in that. And of course, we do workshops. So this is today's workshop. We're always looking for suggestions for future workshops to do because we want to meet people's needs. We don't know them inherently, intuitively what everyone wants to know. So please let us know if there's something you think would be useful to learn about. All right, so now we can get to power analysis. Okay, what's the point of power analysis? Right, so there are kind of two ways to think about power analysis. Actually, sometimes it'll come up to three, but if you're designing a study, and this is kind of the ideal situation, you're designing a study, you want to estimate certain things from the data, and you need to know how big the sample size needs to be, right? And power is one particular way of looking at that. And of course, you want your sample size to be big enough so that you have a decent chance of detecting the thing that you're looking for. right? If you have way too small of a sample, and you can run your grant and do all the methods properly, and then you don't learn anything, and it was kind of a waste of time. But if you plan properly and collect a big enough sample, then you'll be great, probably. The other way to think about it, of course, you don't want to collect too big of a sample, right? If you say, I want my sample size to be 1 million, and that's way overpowered, then your statistics will all work out great, but you spent a lot more money than you needed to spend. And of course, there are always trade-offs, right, in terms of how you spend your money, and there are limits and grants and things like that. So, or your time, right, if you're collecting the data yourself. So getting the power right is pretty important, because you want to make sure you have a big enough sample size. You don't want to overshoot too much. Well, it's generally good to be conservative and get a bigger sample than you think you need. The other thing is that when after you run a study, or if you can't really control how big a sample size is, then you want to have some sense of what this particular sample is good for. You want to know, like, how big of an effect would I be able to see with this sample, with this design, with this research design? What kind of sample could I see? What kind of effect could I see? And that can be important even after you do all your statistical analysis, you estimate everything that you want to estimate. It's useful to know what the power is. And the reason is because very underpowered studies, if you get a significant effect, despite the low power, that effect is probably overestimated. And there's a decent chance it's in the wrong direction, right? So understanding the power of your design, of your research design, can actually give you a better sense of what you learned, even after the fact. And also, of course, if you don't get any effect, which is more likely with a small sample, then a power analysis can help you understand, okay, well, does that mean that the true effect is like 0 or really small? Or does it mean that the true effect is big, but I just didn't have a powerful enough sample, powerful enough design to find it? We're going to talk mostly about this first question about determining the sample size a priori. But a lot of this applies to the second scenario too. Right. So the background of power analysis is hypothesis testing, null hypothesis testing. This is back to kind of stats 101, right? So you have your scientific hypothesis, which is, my intervention boosts students' test scores. That's your scientific hypothesis. Then, from that you get a statistical null hypothesis, which is kind of the opposite. And that is that there's no effect at all. That's the null hypothesis. Null hypothesis can really be anything. It can be the effect is 5. That could also be a null hypothesis. But most of the time, the null hypothesis means there's no effect, right? And the way significance testing works is we say, okay, well, let's assume that null hypothesis is true. Now, is the data we gathered plausible? Right? If, I assume the null hypothesis is true, and then, well, okay, does that make sense given everything that I'm seeing, right? So it's kind of the p-value is, the probability of having a test statistic value greater than or equal to what you saw, given the null hypothesis being true. But anyway, at the end of the day, you come up with a binary decision. So either you reject the null hypothesis, meaning you found an effect, or you fail to reject the null hypothesis, meaning, okay, we can't say that there's no effect, but we don't actually know what there is, right? Fail to reject technically doesn't actually tell you anything, right? Only that your design wasn't powerful enough to detect whatever effect was there. Right, so then we talk about these two errors. There's type 1 error, which is I think there's an effect, but there actually isn't. And type 2 error, which is I think there isn't an effect, but there is. And I could never remember which one's which. And the only mnemonic that I actually works for me is that the way null hypothesis testing works is that it you set the type 1 error rate. You say, I'm only going to, when the null hypothesis is true, only 5% of the time will I say that the null hypothesis is false, right? Only 5% of the time when the null hypothesis is true will I say that there's an effect when there really isn't. So that's kind of the type 1 error rate is the one we control, and then we try to minimize the type 2 error rate. So type 1 error rate is like the main one. And that's just a historical thing. You could debate whether that's the right decision or not, but that's how things have historically developed. This is a cute, right, cute illustration. So telling this man he's pregnant is a type 1 error. Type 2 error is, this clearly pregnant woman telling her, she's not pregnant, right? Anyway, that's cute. Well, so the power is now the probability of rejecting the null hypothesis when the null hypothesis is false. So if there's a true effect, then the power is what's the probability you'll reject the null hypothesis? What's the probability you'll have a p-value that's less than 0.05? And it actually is a function of what the true effect is, right? If the true effect is 0.0001, then the power is going to be very, very small, right? If the 0.05, right? If the effect is large, the power will be much higher. But so really power is a function of what the true effect is. But when we talk about the power of a design, we have a particular effect size in mind, and we want to know what the probability of detecting an effect that size is. What's the probability of rejecting the null hypothesis? If you think about what about a design, affects the power, then it's really kind of the whole study design. Is it randomized controlled trial? How did you randomize? Did you randomize students? Did you randomize classrooms? Did you randomize schools? Those sorts of things. Is it a repeated measures design? How big the sample is, obviously. So if the sample size might be the number of students, or it might be the number of schools, or it might be the number of classrooms, right? There's all sorts of ways to think about sample size, really, turns out. Now, like, what hypothesis are you testing? Are you analyzing the data? And then, okay, the type 1 error rate, almost always you set to 0.05. If you set it to something lower, then your power is going to be lower. If you set it to something higher, your power is going to be higher, right? And then, so that's all stuff you can control. You can kind of decide what you're going to do and do it in such a way that you get the power you want. Then there's stuff you don't know. So kind of the magnitude of the true effect is going to impact your power, right? That's kind of something you can decide. We'll talk a little bit about that more. But then there's other parameters of the true data generating model. Where this data came from, which is stuff you just have to guess at. And that actually I find to be really difficult. I'll say a little bit more, but I think that's the hardest part about power analysis, is this guessing at these things. All right. Okay, this is kind of what we said before, right? If there is a true effect, we want to be able to see it. We want to have a high probability of rejecting the null hypothesis. If there's no effect, then we want to know why. We want to know, is it that we just didn't have enough power? There is an effect, but there wasn't enough power, or is it that there actually isn't an effect, right? So if you have, if your study is powered well enough, then a null effect, failing to reject the null hypothesis, actually has some meaning. You can learn something from it. Even though earlier I said technically it doesn't tell you anything, if you have a sufficiently powered study, it does tell you something. Right. Okay. I don't know if anyone else finds this useful, but I like when you think about power, I think about like a powerful microscope, right? So powerful microscope, you're trying to find an amoeba in some sample, right? This like one-celled organism. And hey, if it's powerful, then you can see the amoeba, and then sometimes you can even, look inside of it and see like how it's shaped, and maybe organelles inside of it, cool stuff. If you have a less powerful microscope, right, then, okay, well, maybe you can see someone's finger, So, a powerful study you can detect very small effects and sometimes even dig deeper. An underpowered study, which is like this less powerful microscope here, then you can only see really big effects like a finger, really big things. But at the same time, you don't want to. If you're looking for fingers, you don't want to buy an electron microscope, right? That's what I was saying. Don't spend $1 million on your study if the thing you're looking for is really big. Anyway, I like when you think about power, is like how well can you see things? How well can you see small things? I don't know. I like that. All right. So I said a little bit before about kind of the two scenarios, but really there's a few different types of power analysis. One of the programs we're going to look at a little bit later, G-Power, actually gives you, I think, like 5 options or something like that. But I've only ever used 3 of them. I don't know what one of the other 2 are. But all right. So if you think about it, there are kind of 3 really kind of central quantities that we're interested in. One of them is the power of the study. One of them is what the true effect is. And one of them is the sample size that we choose. And kind of the idea is that you specify 2 of these and then figure out what the third one is, given all the other stuff that you have to just kind of guess at or decide on, right? So sometimes you're given a particular study and you have an idea of what the true effect is, and I say, okay, well then what's the power? Sometimes you want 80% power. That's like the standard thing, 80% power. Should tell you guys now when you apply for grants, they want to see 80% power, right? So you want 80% power. You have an idea what the true effect might be, and I say, okay, well, how big of a sample do I need to see that? And then the last one is, okay, I have my design already. I've designed my experiment. I know how big of a sample it is. And I want 80% power. How big does the effect need to be in order for me to be able to see it with high probability? Right. So they call that the minimum detectable effect size. And that's sometimes an important quantity. We'll see that comes up especially in Power Up, which is another program we'll look at. All right. I just say very briefly, there's as statisticians and everyone else who does quantitative methods is starting to move away from hypothesis testing because it has all sorts of problems that we're not going to get into here. But there are a lot of problems with p-values and hypothesis testing. A lot of people are saying, why are we talking about testing? We should talk about estimating things, right? And from that perspective, power analysis, an alternative to power analysis is precision analysis. It might have other names too, but the idea is I want to estimate the effect, and I want to estimate the effect with a margin of error of like 0.1 or something like that, whatever the units are, right? You specify a margin of error, and then you design your study such that this is the expected margin of error. Actually, it turns out, for various mathematical reasons, it comes out to be roughly the same idea as power, but it's a kind of different way to look at things, which I think is kind of neat. We're not going to talk about it. It's not something that people are doing a lot, but keep your ears open when you start hearing about these things. Maybe next year I'll do it on precision analysis instead of power analysis. That'd be kind of neat. All right. Just to illustrate things, I wanted to do kind of a little simulation in R. Now, this isn't an R workshop. I don't know, have any of y'all used R before? Okay, well, that's good. So if you haven't, I hope that I can make clear exactly what's going on here. So the little arrow assigns values to names, right? So, and this is RStudio, so it's kind of a wrapper for R. So set n equals 100, that's a sample size. F is the true effect, 0.2. And then I'm going to make up some fake data. Rep just kind of repeats a vector over and over again. So, and R norm generates random standard normal deviates. And so then, and treatment, this is going to be a vector of ones and zeros here. So, you know, you can look at sex, just a bunch of M's and F's, and pretest is a bunch of numbers, and treatment is a vector of a bunch of ones and then a bunch of zeros, right? So it's orthogonal to sex if you're worried about that. Okay, so now I'm going to collect a vector of 1,000 p-values. Start p-values is now it's just going to be a vector of 1,000 NAs, right? The first head prints out the first six, you know, the first six elements of something. So just NAs. Okay, so now as I moves from 1 to 1,000, I'm going to generate a new fake outcome, which is, you know, 0.3 if it's female, 0.7 times whatever the pretest is, and then the effect, which I set to 0.2 up here. The effect, if they're treated, you add an extra 0.2 to y, and then some more random numbers at the end here, so that it's random. So generate a new effect 1,000 times. Each time, LM, it runs an OLS model. So each time we're going to run an OLS model, and then extract the p-value that we're interested in here, and put it in that slot of the p-values vector. So run all of that. Oops. Okay, well. Oh yeah, so it's not letting me do the show you the histogram here, but that doesn't do it. Okay, well. Oh, here it is. Let's try this histogram. So here are all the p-values. Here's the histogram. This is actually, I don't normally use RStudio because it's annoying in this way, but anyway. So there are a bunch of p-values that are less than, they're small. And we see what's less than 0.1, but there are a lot of big p-values too, right? If you look, so the mean this is the mean of the binary variable of whether the p-value is less than 0.05. So a mean of a binary variable is a proportion, right? Proportions of ones. So the proportion of times that the p-value is less than 0.05 is 18%. 18% of the time the p-value is less than 0.05. That's an estimate of the power. Right? That's basically the power, right? So you imagine you ran your study 1,000 times. Under these scenarios, if the true effect was 0.2, if this was like the true data generating model, and this is your, and you're using OLS to estimate and things like that, then 18% of the time you'll have a significant effect, and 82% of the time you'll not have a significant effect. Right? That's your power, basically. Make sense? We can play around here. What if the effect were 0.8, right? Let's do it again. Just set the effect to 0.8. We can leave everything else the same, and run the simulation. Here's the histogram of p-values. Okay, well now they're all small, right? There are basically no big p-values here, and 98% of the time we found an effect. So, okay, when the effect size is big, 100 is enough to see it. The effect size is small, 100 is not enough to see it. Another thing we could do is put this back to 0.2 and, make the sample size much bigger. So actually now we got to run everything again because it has to be the right size. Now we can run it again and see what happens. So, yeah, okay, p-values are all pretty small.
Hello,
right?
Professor. I'm sorry to disturb, but we can't see the screen.
You can't see the screen?
Yes, this is like a frozen screen, so we can't see the data.
PowerPoint?
Oh, yes, I have my PowerPoint.
Oh, so you're seeing my slides, you're not seeing the R.
Yes, I'm seeing by.
Okay, I'm sorry. I thought I told it to share the whole screen. Okay, sorry. What if so I was about to finish the simulation thing, just do that. So now it's going, is it going blank for you?
It's still a frozen screen. I mean, I can't see the share screen.
Huh. What if I do this?
Oh, yes.
Okay, and now you see it.
Yeah, I can see it now. Thank
All
you.
right. Okay, well,
Thank you so much.
it's a little bit too late, but this is good for other things. Yeah. All right. So I can send out this code if that would be useful, and you can play with it some more. I wanted to run that simulation. So I have found personally in my in my experience, I find it easier to understand simulations than kind of abstract mathy stuff. And I'm pretty good at math, but all the same. So I figured maybe I should do a little bit of that to make it more concrete. And now I gotta go find where we were. Okay. So, right, now we're gonna get a little bit down to brass tacks and talk about kind of the steps of power analysis. And along the way, I'm gonna talk about these are real examples of power analysis that I've done since I've gotten here on people's grants. They're a little bit simplified, but so one of them I'll call the PTSD study. There was someone, she wanted to study 3 different treatments of post-traumatic stress disorder for veterans. And the question was, okay, well, how big of a sample ought we to gather for this study? The second example was someone wanted to run an RCT, a randomized control trial, for a new instructional model. She had this idea about a better way to teach science to bilingual students. I'll call that the bilingual study. So I'm going to talk about the PTSD study and the bilingual study. So there's the bilingual study, and it was a pilot study, which, so when you develop a new thing, they say, well, okay, run a small study to see what happens. Now, pilot studies ought not to be used to estimate effects. They're not for that. What the point of a pilot study is to see, okay, well, does it work? Can you deliver this thing that you're saying you deliver? Right? What snags do you hit along the way? Can you recruit people to be in an experiment? All that stuff. That's what a pilot study is for. Nevertheless, everyone wants to estimate things with pilot studies, and so then they ask you, what's the power of your pilot study? And so that was so in this scenario, we weren't trying to figure out what the sample size was. That was kind of established based on the background of the grant. Instead, we wanted to see what was the minimum detectable effect size. How big an effect of an effect could we see with this pilot study that she was designing, right? So there's the PTSD study and the bilingual study, and we can go through and we'll go through all the details along the way. This is a summary slide, right? This is the steps for power analysis. First, what hypothesis are you testing, right? Then, how are you designing your study, except other than the sample size, right? That might come later, but is it an RCT? Is it how is the RCT structured? Are you gathering observational data? Whatever, that's a study design. Then, okay, how are you going to analyze the data? Are you going to use regression, some non-parametric method, et cetera, et cetera? Okay, then the question is, what effect size are you going to power for? I'll say a little bit more about that, but how big of an effect would you like to be able to see? And so it's actually a design decision. And then you have to kind of guess at all the other parameters, and I'll explain what that means in terms of examples as we go through. And then once you get all that, you kind of stick it all into your power analysis engine, and it spits out the numbers you want. Sometimes it can be a little bit more complicated, but most of the time it's just plug and chug. Now, if you don't like the answer you got to number 6, then you can go back and mess with 1 through 4. Maybe I need a different design. Maybe I need a different data analysis method that's more powerful. Maybe this hypothesis is too hard to see in this data set, et cetera. But, these are definitely like mutable. And All right. Okay, choosing a hypothesis. So like, what are you interested in learning? What do you want to estimate, right? Actually, this is a little bit of a pet peeve of mine. People come in saying, okay, I want to run an ANOVA, or I want to test this. And I think to myself, why are we interested in testing? Like we want to learn something, right? We want to estimate a quantity. And then we can kind of wonder, well, how much do we actually know about this quantity? Are we sure it's not zero? That's testing. But I always want to start with, okay, well, let's estimate something. And then we can think about tests afterwards. But all right, so what do you want to estimate? What does a null effect mean? Does it mean the thing you're trying to estimate is zero? Most of the time, that's what people mean when they mean null, right? The zero effect. It can be anything. And of course, you want to make sure that it's well defined and that this is actually something that you can learn from a data set, right? So for a good example would be, I have a hypothesis, my scientific hypothesis. This isn't a null hypothesis, but my scientific hypothesis is that my intervention will improve post-test scores when compared to standard practice, right? And so then you can kind of estimate an effect. Okay, how much does it improve scores? And a null effect would be no improvement. So that's a nice hypothesis. You might say a bad example would be like my intervention helps students learn algebra. So that's a good place to start, but then you have to be more precise when you're going around, when you're trying to define data analysis method. All right, so here are the actual examples. In the PTSD study, there was this hypothesis that the three treatments differ in their effects on the CAPS-5 scores, which is like a standard PTSD measurement, right? The first question was, do these three evidence-based treatments actually have different effects, right? We can test that one, see if they're all the same or they're different. And then we can try to estimate what the difference between the effects is. A null effect would mean, no, they're all the same. They all work the same. In the bilingual study, the hypothesis is that the new instructional method improves scores on a biology post-test relative to business as usual. Okay, you can read it. I don't need to read you the slide. But the null effect is that no, it doesn't help anyone. Okay, step 2 is the study design. What data are we collecting? What's the outcome, right? What are you going to collect in the outcome? What background covariates, are you going to collect data on people's, gender, pre-test scores, SES, whatever it is. Sometimes they're mediators or moderators. I'm not really going to talk about that, but that's part of it. And then how are you going to collect it? Are you running a randomized trial, observational study? Is it a survey, et cetera, et cetera? And how in a randomized trial, we'll talk a lot more about this, but who is being randomized and how, that ends up being important. And then, of course, if you have a longitudinal study, that's important. So here are the examples. In the PTSD study, there's, in the most basic form, we're just gathering this outcome data from three groups of veterans who had the different treatments. For the sake of the power analysis, we kind of assumed that they were being randomized between treatments, although that wasn't actually what was happening. We could have done something more complicated in which that wasn't the case, but for this one, we wanted to keep it simple. So we assumed they're randomized for the sake of the power analysis. And then, and so that was kind of the design there. For the bilingual study, the high schools were being randomized, not the students, but 5 high schools were being randomized to treatment and 5 to control. And then you have to gather data from all these students nested within classrooms, and you get the post-test scores, and we gathered a bunch of covariates, the grant didn't get funded, but we would have gathered a lot of covariates, et cetera, et cetera. So that's all important. Oh, you guys are seeing all this. Okay, well, anyway. The data analysis method. So, okay, this is like, my bread and butter. I'm a statistician. This is what I was trained in. But it's actually not, it's kind of orthogonal. It's important for power analysis, but a whole different set of questions. How are you going to estimate this quantity? And you obviously want your data analysis method to match the research design and to match the hypothesis, right? And that's all very important. But for another day. So, for the PDSD study, the method was doing a one-way ANOVA. And for the bilingual study, we used a hierarchical linear model or a multi-level model, a mixed model. They all mean the same thing. Okay, now here's where we get interesting. What effect size do you have power for, right? So there are a few ways to look at this. One of them, a lot of times the inclination is, well, I want to guess what the true effect is, and then I want to power for that, what I think the true effect is. I would argue that that's not actually what you want to do. Why? Because, if it's a little bit smaller, then your power is lower than that, right? It's not, and anyway, the whole point of your study is you don't know what the true effect is. So why would you, come with some preconceived idea about this quantity and then power your study for that, right? If you're off by just a little bit, it can ruin your power, and that's not what you want to do. Instead, what I would say is, okay, well, what's the smallest effect that I'd like to be able to see? So one way to think about that is anything smaller than that is like not an important effect. If this boosts students' test scores by 0.0001 standard deviations on average, that's not an interesting effect, right? So you want to find kind of the smallest interesting effect. So then the question is, well, what's the smallest interesting effect? And that is a difficult question to answer. We could talk a little bit more. Well, okay, I'll explain what that is in the next slide. But another thing about that is like, okay, so now you didn't reject the null hypothesis, right? P equals 5, whatever it is, 0.5. Now, okay, what kinds of if you powered your study to detect an effect size of 0.2, and now your p-value is large, it probably means that the true effect, okay, I mean, you can do statistics about this, right? They're very formal about it, but there's a good chance that the effect is smaller than 0.2, right? If it were bigger than 0.2, you'd probably get a small p-value. That's the whole point of power analysis. So, when you choose kind of the smallest meaningful effect size, you're also thinking about what is my null result going to rule out? What kind of effects is my null result going to rule out, right? Actually, in social science, almost nothing is zero. There's, the null hypothesis, strictly speaking, the null hypothesis is almost always false. Everything affects everything somehow or another, right? But, often, very, very often, the true effect is not zero, but really, really small, And so what do we mean by really small, What counts as a small effect and what counts as a big effect? So let's talk a little bit about this. So there's some more background here. Okay, we're going to talk a lot about effect sizes. Now, there's a whole literature on how to define effect sizes for different kinds of effects and different designs and this, that, and the other. Again, we're not going to go into that here, but just briefly, the most common effect size measure that I see in education research is like Cohen's d. And that is, it's like you imagine you're comparing two groups, treatment and control. And you estimate an effect, and then you divide the effect by some sort of standard deviation. Now, the standard deviation, so the effect is like what you're trying to measure. Maybe it's a difference between treatment and control, or it could be a regression coefficient or something like that. The standard deviation is kind of the standard deviation of the outcomes, not accounting, after you account for whatever the true effect is, So it might be the standard deviation of the control outcomes, so there's no effect for them, right? Because it's just control people. Or you could pool the two standard deviations in the two groups. There's all sorts of ways to do it, and there's fancy things you can do to Hedges G, which is better than Cohen's D, but that's this is the basic idea. is that you take an effect on some measure, and then you divide it by standard deviation. And the reason you do that is because 3 points on the sales algebra post-test doesn't mean anything to anybody. But if I know how people in general tend to vary on the sales algebra post-test, then I say, well, the standard deviation in the group is 5 points, and this affected people's scores by 3 points. Then I say, okay, well, that's a pretty decent size effect, in terms of standard deviation. So that's why we divide by standard deviation, to kind of give meaning to units that otherwise might not have any meaning to people who aren't familiar with whatever measure you're using, right? On the other hand, if it is a meaningful measure, so like let's say I want to estimate an effect on SAT scores, most people who go to college take the SAT, and so we know what a 700 is, or what a 600 and a 500 and a 400 is. If I say something has an effect of 50 points on the SAT, okay, I know what that means, right? That is a meaningful number to me, right? So sometimes you want, the raw effect is a useful thing to do. So other options, sometimes you just want to look at the correlation between two continuous variables, or if you have two binary variables, an odds ratio as an example, there's F for F squared, which is useful in ANOVAs and other sorts of tests for regression. There are a very large host of others. But yeah, most of the time when I talk about an effect, it's Cohen's d or something related to that. All right, so how do you choose an effect size? You say we want the smallest meaningful effect. Well, what in the heck does that mean? So I think the best thing to do is use theory. Like I have a sense of what practical meaning each kind of effect size would be, and I know what the smallest effect size that has any practical meaning is, not based on data, but just based on my understanding of the world. That's great. That has never happened in my experience. Nobody's ever come to my office and said, an effect smaller than this is meaningless and bigger than that is meaningful. I think that especially in social science, we don't really have a very good understanding of scales. Not because we're not good at math, but because social science is really hard, right? Second option is look at prior literature. I'm studying an intervention on algebra, and I want to know, how do different interventions on algebra tend to work, right? Now, there's some interventions that have an effect size, Cohen's d of 0.3, and those are considered really important, and others that have an effect size of 0.2, and those are considered pretty important. And then, smaller than 0.2, nobody really seems to care. So now I could say, okay, well, 0.2 might be a good thing to power for, right? I did a study. Very, very recently, I was doing a study in the School of Nursing where we were looking at relationships between different biomarkers and symptoms. And I happen to have some pilot data, so I looked at those correlations in my pilot data, and I said, okay, well, there are different classes. There's some with correlation of 0.6, others where it's a correlation of 0.3, and then, middling correlations that seem less important. And so I said, okay, let's power it to 0.3, But of course, that's all kind of, none of this is scientific, right? This is all kind of, it's you can say it's an art, not a science, but I wish I could give you very good guidelines. Do this, 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 this. If it's that, then do this. If it's that, then do this. I can't. And that's going to be a theme, unfortunately, in this workshop. Nobody's figured these questions out, right? We don't actually know how to, there's no good rules for how to choose an effect size. If you don't have prior data on your question, you can look at prior data on other questions. How big are effect sizes on, when you look at kind of education effects at scale, or when you look at, whatever it is, how big of an effect size do we tend to see, or what's the distribution of effect sizes in reality? And for these sorts of things, another way to look at it, and that is that there's a paper from IES about kind of Lipsy, and he says so take effects that people might not know them numerically, but people know, that this is important, right? And then measure your effect size relative to that, So there people talk a lot about the black-white achievement gap, right? Whatever that means, my intervention has an effect that's a third of that, right? Now that's something that at least people think they know what that means, right? But that's kind of a way to anchor things. Take some number that people care about. Another thing people talk about is how much do you improve over the course of a year? Now let's take a fraction of that and see that's the effect size. This is equivalent to 1 year's worth of learning, which is complicated. The last option is, people call this the T-shirt effect sizes. There's a standard list of, I should know this, but I don't actually. I think 0.2 is small and 0.5 is medium and 0.8 is large, right? Those are kind of standard numbers. You can use those. I'm powering this for a small effect, whatever. The problem with those is that it was Kohn, the same Kohn from Cohn's D, he came up with those. He looked at a range of studies in whatever discipline he was interested in, psychology, I think, and said, okay, well, these are the range of effect sizes I see, and this is small, this is medium, this is large. But, in what you're studying, it's a different distribution of effect sizes. So why are you using the numbers that he came up with to study your problem? But if you really have no prior knowledge or no real sense of things, then it could be kind of a last resort option to kind of think about the Cohn's effect sizes. Right, okay, so here are some examples. For the PTSD study, I looked at some previous studies. I said, okay, well, how big how big are the effects of PTSD treatments typically, how about the differences between them? I found a couple of different studies. The Cochrane database of systematic reviews is very highly respected in medicine. And so they look at kind of research studies and evaluate them for their quality and then put the results all together in one paper. So that can be a useful place to look for this sort of thing. I wrote something like medium or larger effect sizes are typical. And so, but let's say that the true effect is 0.1, F equals 0.1 because it was an ANOVA. In the bilingual study, I didn't bother with any of this because we were trying to estimate the medium detectable effect size, minimum detectable effect size. And so I didn't try to figure out what effect size to power for. That was what we were estimating. So didn't have to do that. Okay, this is even harder than choosing an effect size, and that is guessing at the other parameters. And what that means depends on what your data, what your design is. It could be like how well do the covariates predict the outcomes, how ICCs, which we'll talk more about later, all sorts of other things that, if you think back to the simulation example I showed you, I put in an effect of sex and I put in an effect of the pretest, right? And then I kind of assumed that everything else was independent, those are the other parameters that you need to know. All right. Actually, that's a nice thing about simulation studies is because when you do a simulation study to figure out power, you have to put in what all the parameters are, and you realize, oh yeah, I don't know what those parameters are. I have to guess at those values. Everything that plays a role in your analysis, you need a number for that. And in some kind of standard scenarios, they can reduce all of the different disparate numbers into one kind of summary statistic that is all that matters for power. And we'll see examples of that later on. But you have to come up with numbers for this. Do you have a question? Oh, okay. I thought you were raising your hand.
No, sorry.
Yeah. Does anyone have any questions, by the way? I've been just rambling on. Am I going too fast or too slow or good? All right. Oh my, it's almost 2. Okay, well, we're almost where it's supposed to be at 2, so it's good. All right, so how do we know what these numbers are? My favorite is when we have pilot data. So someone gathered data on the sort of thing before, and then I can kind of, run the model that I was going to run in the experiment on the pilot data and kind of get at least decent guesses at what these numbers might be from the pilot data. I just said you shouldn't use pilot data to estimate things. I know, I'm kind of contradicting myself. But you're looking for a number somewhere, and this is the best you can do from the pilot data sometimes. I think that could be useful. And, there's hand waving involved. This isn't actually what I'm trying to estimate, but it's, similar, and maybe I can use this number. At least it's, a little bit more objective, right? Another option is sometimes people publish these numbers, so that's great. You can find the paper where someone studied something like this and published the number you're looking for, and then use that. And that includes, there's some kind of published databases. There's this number that I've referred to a little bit before, the ICC. So these two education researchers, Hedges and Hedberg, published a bunch of papers where they kind of give you ICCs for all sorts of different scenarios and covariate R-squareds and et cetera, et cetera. And I'll give an example from that too. But that's great stuff. Another thing is to be conservative. This is what I mentioned before, right? Don't choose the most optimistic value from your ICC numbers. Choose maybe the less optimistic value, but also don't assume something crazy out there, because then you'll end up with a much too big sample and you'll waste your money, right? Or waste your time. And so there's that too. Okay, well, what values are conservative and which ones aren't? Try it out with a bunch of different values and see what it looks like, right? Plug in different values and see how that changes your power along a reasonable range of possible values. Right, okay, so here's an example. In the PTSD study, I kind of wanted to do it quick and dirty, so we just there were no covariates, everything was independent, all of that nice simplifying assumptions, and so there were no more parameters. I didn't have to guess at any parameters. That was lucky. Well, it wasn't lucky. It was me being expedient. For the bilingual study, there were a bunch of different parameters, but really what it boils down to is this ICC that I keep talking about, and I'm going to explain what it is when we get to it. But this is ICC number, and I had to find that. And also the R-squared from covariates, which is what proportion of the variance in the outcome is predicted by, not by your treatment, but by the covariates, by pretest, sex, whatever it is, And I got these two numbers from this paper, Hedges and Hedberg, 2003. But actually it was a little bit more complicated. I was interested in science tests, and they didn't list anything for science tests. They only listed math and reading. And I was interested in results from Texas, because that's where the study was going to take place, but they didn't have Texas on there. They had it by state, but they didn't have Texas. So, okay, I looked at the average for all the study, average over the states, that they did look at for grade 10, and I looked at a math test. And not science, it's math, so this is kind of trying to illustrate the difficulty of the problem. Even in a situation where these are standard parameters, that someone's published a study listing all of them, I still can't find the thing I need. So you have to wave your hands. and choose something. There was another issue. They had the ICCs for district and school and student, but I wanted the ICCs for school and teacher and student. So that's another thing. And I don't actually, not sure exactly what I did there, but you have to kind of making stuff up. And, you know, if power analysis weren't so important, I would kind of say, this is a bunch of baloney. You know, well, you're making all these numbers up and giving and plugging them through a machine and then telling me something. But power analysis is super important, and it's really actually very frustrating to me that there's no good way to choose some of these numbers. But and I think, you know, there ought to be more research on it too. But in the meantime, you have to do the best with what you have, because you have to do this. Right? You have to choose a sample. You know, the better, the more thought you put into choosing a sample, the better. But at the same time, there's a lot of hand waving, a lot of guesswork that goes on. Right, again, I wish I could tell you these are the steps you follow to choose your ICC or to choose your whatever, but I can't. So, you know, in general, also the better you know the subject area, the better you can figure these numbers out. So there's that too. All right. Okay, so I'm going to go through a little bit of the last step is like plug and chug. Okay, so we'll get to that later, but here's like a long list of kind of pieces of software you can use. You know, we'll talk about GPower. SimSem is like in R, and it does like, if you're interested in like structural equation modeling or, you know, factor analysis, it'll do that. PowerUp we'll also talk about. Optimal Design is, some of the same people who worked on PowerUp did Optimal Design. It's a nice kind of, it makes nice plots for power as sample size changes or whatever. It also has, Optimal Design has something for within repeated measure studies. So you follow the same people over time and see whether their test scores grow or whatever. The test scores grow differently in two different groups. So Optimal Design has that. But it only works on Windows machines. So if you have a Mac, you're out of luck. They tell you can use like a virtual machine. And I tried to do that so that I could show you Optimal Design for people who have Macs. But I couldn't get it to work. So, you know, anyway, it might be something to look into. A lot of this PowerUp gives you a lot of the same stuff, and that's just an Excel spreadsheet. We'll see. So that's nice. And then, you know, if you use M+ for structural equation modeling, that has functions to run Monte Carlo studies, which is nice, simulation studies. I don't know what PASS is, but it's another thing. I used some of their literature recently. Used some of their literature recently, which was very useful actually. But so you could, if you want to know how to do a particular power analysis and what the equations are, you can download and then plug in the numbers to the equations yourself. So that's actually kind of nice. And then actually the NIH has their own power calculators for certain kinds of designs because they want people to submit good grants, right? So they put, you go to their website and, you know, click all the options and put in all the numbers and it'll tell you the power. So that's also kind of nice. Bless you. Anyway, we're going to talk about GPower and PowerUp. And I'm going to show you examples of that. But first, we will take a break for, I don't know, 3 minutes or something. If anyone needs to go to the bathroom. Or let's just say 5 minutes to keep it round. So that means that on my watch, at least, it's 2:10. Or, sorry, yeah, 2:10. What if I pause the recording? I really hope I'm recording this. Otherwise, people who wanted a recording are going to be disappointed. Don't need this. All right. I don't know how to post the recording, so everyone watching at home is, you know. Well, I think we can start again. Oh, oh. Okay, well, let's get started. Okay, so I'm going to talk a little bit about two pieces of software, like I said, G-Power and PowerUp. What about each one? Okay, we're going to talk about G-Power. There's a number of choices you have to make with G-Power. It's kind of types of power analyses, families of tests, and then, for each family of tests or for each test within each family, you have to put in different numbers. And so we're going to talk about how to do that. But before we get to that, did anyone have any trouble downloading G-Power, getting it started? Or does everyone have it? Okay, excellent, good. If you don't, that's fine. You can tell me. Okay, good. Okay, yeah, this is the website you saw when you went to download it. Blah, 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 blah. Right. So, like I said, it gives you 5 types of power analysis. A priori, which is choosing the sample size. Okay, sorry. Like you can see here, there are 5 bullet points. Some of y'all might be better at counting than I am. It gives you 5 types of power analyses. Only 3 of them, the bold ones, are the ones that I've ever found reason to use. So that's the only ones I'm going to talk about. But those exist, and you have to choose which one you're doing. So a priori power analysis is, I should have put up the little nice figures I made before. Anyway, you put in, this is like when you want to figure out what sample size you need. So you put in the effect size you want, the type 1 error rate, which is almost always 0.05. So just put in 0.05. And then the power that you want, which, in our world is generally people want 80% power, so put in 0.8. Although the default in G-Power, for whatever reason, is 95% power, which is better, but then you need a bigger sample or smaller effects or something. And then what it tells you, and then it'll tell you the sample size. Post hoc power analysis is like you already designed your study, and this is what you got, and now you want to know what the power for the study for particular effect size is. This might be a good point to say a little bit. I don't have this on the slides anywhere, but about there's something. Every once in a while, people do this thing, and I totally get the temptation, but I think it's a bad idea. So do a lot of other statisticians. You run your study, you estimate an effect, and then you use that estimated effect to see what the power is. What would be the power to detect an effect of the size that I observed? Makes sense. You have a number for the effect size now, may as well plug it in, right? So the problem with that, there might be a couple of problems with that, but to me, the main problem with that is like I said earlier, once you, if you have an underpowered study and you get a significant effect, then that significant effect is very, very likely to be way overestimated, right? So, you run a study on like 10 people, right? And you see an effect size of 3, which is like crazy, right? So, okay, that's probably not right. That's probably way too big. And there's a mathematical reason for that. Is because, statistical significance is a function of the effect you measure and the standard error. And so if you get statistical significance in an underpowered study, then either the standard error is small or the effect is big. One of those 2 things has to be true to get a significant effect. And so Well, there's a good chance, or both, right? Both of them could be true. So there's a good chance your estimate is going to be too big. Another thing is that it might be in the wrong direction if your study is underpowered, right? Oh yeah, I was gonna ask you, see if maybe this is obvious, but if you have, remember the simulation study I was running, right? So you set the effect to some number and the sample size is some number, and then you estimate the power based on that. What if I set the effect to 0? Then what would I get for the power? What proportion of the time would the p-value be less than 0.05? What would I get for the power if the effect were set to 0? It would always be less than the p-value would always be less than. How often would the p-value be less than point? Did I say how often would the effect be less than 0.05? I mean, how often would the p-value be less than 0.05 if the effect were set to 0? How often would the p-value be significant?
Every time?
So that would mean that there's no effect, but I'm detecting an effect every time. So we don't want that.
Yeah.
So 0 is not 0. That would be nice, but 0 is not right either. Right? So think about type 1 error rates and type 2 error rates. And so the type 1 error rate, a type 1 error is, right, we think there's an effect when there really isn't one. Right? Here there isn't one. So if I say there's an effect, that's a type 1 error. Now what's the probability of getting a type 1 error? Very close, but the opposite. 0.05. 0.05 is a type 1 error rate, right? So that's what we set it to. If the true effect is 0, 5% of the time we're going to say there's an effect. That's what type 1 error rate is. I should have shown that. I meant to do that in the simulation study. We could try it out. It works. I did it. If you set the effect to 0, 5% of the time you see an effect, right? And that's something that we, for whatever reason, probably a bad one, we've decided that that's what we should set as our type 1 error rate. So 5% of the time, if there's no effect, 5% of the time you'll think there is an effect, right? Now, half the time, half of that 5% of the time, 2.5% of the time, you're going to think there's a positive effect, and 2.5% of the time you're going to think there's a negative effect, right? If the null hypothesis is 0, right? Then half the time you're going to think each one. So if you think about it, if the effect is positive but really small, then half of the significant, it's going to be a little less than half of the significant effects are negative, but not that much less, right? Maybe 40% of the time the significant effects are going to be negative, even if the true effect is positive, right? So you get these kind of, in underpowered studies, a lot of the time when you have a significant effect, it's in the wrong direction. And it's almost always way too big, So anyway, the reason for all of that is that don't run a study, take the effect you estimated and plug it into a power analysis and say, hey, we were powered enough to detect this, right? That doesn't actually tell you what you want to know. Instead, you have to think about well, what would be a reasonable effect here? And then plug that in, Anyway, off my soapbox and back to talking about types of power analysis, right? So you have a particular study that you've planned with a particular effect size in mind, not the one you estimated, but you have it in mind. You can plug it in and get what's the power for your study, all right? And then they call this the sensitivity power analysis. This kind of comes from in biostats, you have a test that has sensitivity and specificity. So this is kind of like, how sensitive is my study, meaning how big of an effect size am I able to see? In other words, that's the minimum detectable effect size. What's the minimum detectable effect size at a particular power level, at a particular type 1 error rate, and a particular sample size? What's the smallest effect I could see? Right. So there are a lot of families of tests. There's exact tests and F-tests and T-tests and chi-squared tests and Z-tests, and you have to know which one to look at for the particular test you want, which is kind of annoying because you don't always know exactly what family it's in, but you can always just kind of scroll through them and look at all the options. It takes a little bit of time. Okay, we'll go through an example with the independent samples t-test. But you know what, perhaps I should actually do this in actual G-Power, and you guys can follow along with me, even though it's all on the slides. There's G-Power, there it is. Okay. So you guys following at home? Those of you following at home, can you see the G-Power that just came up?
Yes, I can.
Excellent. Good. All right. So here's G-Power. Looks like I already it's got things I stuck in here already. Maybe not. So you want to do a two sample t-test. Like let's say you gather data from controls and from treatment, and you want to compare them. So here are the family of tests. You can go on here, and all y'all, I recommend that you open G-Power and do the things that I'm doing, because then you'll get your mind around it. So click on t-tests, because that's kind of, and then there are a million options here. But we want the difference between two, not dependent, we want two independent means. So dependent means is like matched pairs. If you have kind of before and after, right? We'll see that later. But now we want two independent means. Now we have to choose the which kind. Let's say we want to look for a sample size. I didn't talk about this at all, but do you want a one or two tailed test? There's a so a one tailed test means that so like I think that my treatment improves scores, but let's say my treatment gives you is like 100 times worse than the control, right? Then the p-value will be 1. I won't detect anything. I won't see it, right? One tail test means you only see effects if they're in one particular direction, right? If it's in the direction that you don't expect, your p-value will be non-significant automatically, right? That's a one-sided test. Of course, you get something from this, right? It's always trade-offs. It's you're more likely to get a significant effect in the direction you expect if you do a one-tail test, but you won't see anything in the other direction, right? That makes sense? Yeah. So anyway, almost all the time, the standard is to do two-tail tests. That's what kind of is expected in the literature, because they know that if you were to see in that, you can't do you're cheating if you do two one-tail tests and report whichever one is significant, then you're cheating, right? And they know that if you find a negative effect, you're going to report it. They say, well, then you should do a two-tail test, right? So that's kind of the standard. There are people who say we should move away from that, but anyway, that's not what most people do these days. Okay, so you have to put in your effect size, and this is a Cohen's D. That's why there's a little d there, and 0.05 is the type 1 error rate. Now, most of the time, power is they want it to be 0.8, so we can set that to 0.8. Now, allocation ratio means like we have two groups here, and one of them, are they the same size, or is one twice as big as the other? So one means that the two groups are the same size, because this is kind of the ratio of the two sample sizes. Actually, it just occurred to me now that I'm saying this, I wonder if you get the same answer if you put in a 2 and if you put in a 0.5. I would guess that you would. We can try it out. But and then you calculate, and it gives you the total sample size it says you need is 128. Actually, so the sample size is a discrete variable. You can't have 128 and a half people, right? So it actually gives you the smallest number that would give you at least the right power, right? the smallest number that would give you at least the right power. And it can give you a little bit more power. It gives you 80.1% power. So that's, I don't know, that is what it is.
What's your effect size?
That's over here. It's half a standard deviation, 0.5. Now, let's say you're not sure about what that should be. You can click on this thing, determine, which is kind of neat. So if I have two different size samples, I could put in the mean and the mean in the two groups and the standard deviation within the two groups. So meaning if I just looked at the standard deviation in one, standard deviation in the other, I'm assuming they're both equal to 0.5 in this case. Or you can, if they have the same sample size, there's another way you could do it. Oh, I guess now you get to put in two different SDs. Calculate, and it gives you the effect size. Now the effect size is 2 because it's a difference of 1 divided by 0.5. And 1 divided by 0.5 is 2. Or if you calculate and transfer the main window, it sticks it in here, right? So this determine button is if you're not sure what this effect size means or other parameters that they want you to put in, then it kind of helps you figure out what you should put there. Right? You can stick in like real numbers that mean something real, and it'll translate that into effect size for you. So that's kind of neat. Wait, I wanna test. Let's see if it's true that putting in 0.5 gives you the same as putting in 2. So it's this 144. It's telling us. What if I put in 2? 144. Okay, good. Yeah. So it doesn't matter how you do. I'd be surprised if it were otherwise. All right. So what's nice about G-Power is that it lets you do all sorts of tests. Let's say instead you want to do a Wilcoxon test, right? Is that one of these? Maybe not. But you do a sign test or binomial test or I guess this just has it for proportions. If you want to test something about a proportion, that's kind of neat, right? If you want to do an ANOVA, that'll be under F tests. And COVA, it's got all sorts of different things that you can do here, all sorts of different numbers. There's a very wide range of tests of statistical tests, so that's all nice. On the other hand, it's a very, very wide range of statistical tests, but very narrow range of designs. You can't have nested randomization things. There are no covariates. It's all just kind of, effect size, sample size, power. That's kind of it, right? So that's, yeah.
What if you had 3 or 4 groups? Does that count in the allocation ratio?
I don't think it lets you do that, but we can see. Then you'd probably want something like an ANOVA, like a one-way ANOVA is as simple, that kind of design. Oh yeah, so here it assumes that all the groups are the same size, right? Yeah. Okay. So yeah, and there are 2 ways to kind of calculate the effect size, right? So that's an excellent question because that's kind of a problem with ANOVA, right? This standard old-fashioned Fisher ANOVA that they may have taught you in Stat 101. It requires you to have the same size for every group. When in practice, that's not the case. And also, it's actually not hard to do the same procedure when you have different size groups. But you can't make the nice ANOVA table and calculate the F statistic by hand like they used to do 100 years ago. Right? There might be a more flexible one in here. I don't know. Okay, yeah. So here's, if you want to do something like this. Another. Well, I don't know. There's another way to think about ANOVAs is if you have a regression where you're just regressing your outcome, your continuous outcome on like fixed effects for what group you're in. And then they can be any size, and then it gives you an F test at the end. And that's what this is, except that I don't think that there's a way you can actually put in how many people are in each group, et cetera, et cetera. Maybe there is. I don't know what happens when you click on specify matrices. Feel free to play around. Yeah.
Why isn't there a spot for standard deviation or some measure of variability in this?
So that's a great question. That's folded into the effect size. Especially like the Cohen's d. So if we look, actually, if you look at where we were before, two independent means, and you go to here. So see, now you can put in a standard deviation for each group. And what it'll do, what it does is it takes the difference between these two numbers and then the weighted average of these two numbers and takes the ratio of those two things. Actually not the weighted average. I think it just takes the average of those two numbers because this forces you to have the same size groups to do that. If you have different size groups with different standard deviations in each group, then GPower might not do that for you. I'm not sure. Maybe there's a way to get it to do it. But does that answer your question?
So what analysis do we have to run to have that variability factor in?
You mean different standard deviations in the two groups? So
even if it's repeated measures.
Yeah, no.
There be some measure of variance.
Right. No, I mean, that's true. So, again, this in this setup, in this particular, there might be, I don't actually know what each of these tests lets you do in this particular software. There might be something that does this for you. I mean, I know like a Wilcoxon test is robust to that sort of thing. So you could do that if you wanted. But if you wanted to do a t-test with, different variances, which is like a standard thing to do, and different size groups, which is also a standard thing to do, I don't know if this will do it for you. Before you collect the data, you don't actually know what those standard deviations are anyway, so you have to kind of, make something up, right? So I guess what I would recommend in that situation is either to do something like this, where you and plug in kind of different numbers. Now there might be some theory out there that tells you that two groups with different sample sizes and different standard deviations is equivalent to two groups with the same size and the same standard deviation if you change those numbers the right way.
You can change the group size in there.
You could change the group size. Oh, can you?
Select the F test and go back to another one. And then just click on the box under size, and you can put whatever number.
Oh yeah, but this kind of assumes that you have the same.
Yeah, but if you click it twice, it'll let you adjust the group size from 5 to whatever you want.
Yeah, but I don't think.
Just like click it again, click the actual one 5 is, and click it again.
Oh yeah. Oops. Okay. Oh, no. Okay. Yeah. Right. But there's only one box here. It doesn't let you do a different standard deviation for each group. Now, I mean, if you have a different standard deviation in each group and for some reason what the standard deviations are, then you ought to have different allocation, right? Then you want to have, more people in the group with a smaller standard deviation, or with a bigger standard deviation, right? You want to sample more from the group that's harder to estimate, a bigger standard deviation. So there might be something in here that lets you do that. I don't know what it is. You could run a simulation. But when I hit something like that, I run a simulation. But that takes more work. Yeah, I don't know the answer and otherwise, other than that. That's the limit that you'll find in software like Power software, is that like there's a finite number of cases that they thought about, and that finite number of cases does not contain all of the infinite possibilities that education researchers come up with, right? And so then you have to either your two options are find whatever case is most similar to the thing that you're going to do and just do that, or to do a simulation study. And by the way, you can always come to my office or to Youngri, and we will help you run a simulation study. So there's that. There are resources for that if you don't want to do it yourself, which I can see why you wouldn't. I'm making it sound like really horrible. It's not actually that horrible. I showed you one just now earlier. Okay, we saw all these things, right? Okay, that gives you a nice plot. Oh, yeah, I guess I could do that too. You can plot, I've never actually tried this one, but yeah, you can, some of the, I'm working off the slides that one of the previous GRAs made, but he did this, Danny Swan. I never did this, but anyway, it's there. All right, so if I wanted to do the power for this PTSD study, right? Now, if you recall, I was going to do an ANOVA. I made that decision, and I needed to compute the required sample size. So that's the type of power analysis, and I decided to power for an effect size of 0.1, and I wanted 80% power and alpha equals to 0.05 type 1 error rate. And there were going to be 3 groups because I'm comparing 3 different treatments. And you press calculate, and you get that you need a total sample size of 969. I wrote 1,000 in the grant because, you always want to boost it by a little bit. But that's kind of that example played out. And I was able to use G-Power because it's a very simple design. Now, y'all want to try a couple of things? I wrote a couple examples you can do. I think it's all kind of straight, self-explanatory here. All right, the first one is choosing a sample size for an RCT. And yeah, okay. Anyway, oh, it's already getting late, so maybe let's spend 5 minutes on this, or less. I'll you guys get it done more quickly, and I can walk around and help you. If you're watching from home and you have a question, you can text me. You can put it in the chat. There's a chat thing up here. There's a chat, and if you chat me, I will try to respond. But I'll also be walking around, so I might not see it right away. If anyone has any questions, feel free to raise your hand or somehow or another snap your finger in the air.
Example. Just two groups.
So this is an ANCOVA test. So I think what you want is a Z. The test family is a Z test. So that's up here. Now you want to figure out which test you want.
So it's like t-test.
Okay, so that's not, that's not one of the options, but because with proportions, you don't do a t-test. It's not a t-test you want because the standard deviation is a function of proportions, and so it's not something you have to estimate separately. So that's why I think it's
And the same thing with that test too.
with an F test too.
With net test, you also
Right.
has the same.
Yeah. So that in that one you're looking at kind of a ratio of variances, but yeah. So definitely do two independent proportions. Now, do you want to do the it looks like the part of the window is blocked. Bottom. If you make it so you want to press which buttons on the bottom of this mask. Maybe if you move going to the left, then you'll see the button pressing on the side. Maybe you can be farther.
Yeah.
You can't press the button. Because, yeah. Oh, but actually, you can turn the proportions here. So maybe you don't need that. And you want to do that. Anyone else have a question? I think we'll go through it together. Okay. Let's go through some of these. But I want to keep this open so we can see it. All right. Okay, so for exercise 1, I said, so here it's like a t-test in that we're comparing the two means, but instead of means, it's proportions. And so proportions are a type of mean. So if you did a t-test, you could be forgiven. But actually, a z-test is even better. And that's because when you have proportions that you don't have to estimate the standard deviation separately. So if you go to z-tests, and now we're looking at the difference between two independent proportions. And that was the whole hard part. But then remember, we typically want a two-tailed test. I didn't tell you that, but that's normally the case. So let's say in the control group, the proportion is 0.6. And then you want it to be at least 10% in the 10% better in the treatment group. So 10% better is well, 5, is now 0.5 because it's something we want to lower. And then we'll set that power to 0.8 because that's like the standard thing. And I guess I didn't tell you the allocation ratio should be 1, but it should be right. Let's do it that way at least. And you calculate it, and you find that you need a total sample size of, almost 800 students for that. That's pretty big effect, 10%. dropping. No, actually, a big effect would be you need less people, but all the same. Did anyone get anything different? No. Very good.
Because I did the wrong test.
Oh, so you could do something similar. There are a bunch of exact tests that let you look at proportions too. Like this one, Fisher's exact test. We can try it like that too. Wonder if it'd give us better power. Probably not. Oh yeah. Hey, you do Fisher's exact test, you need a smaller sample size. Maybe you do that. Anyway, that was exercise 1. And you know what? That's actually a good illustration now that I think about it. Turns out if you use a different analysis method, sometimes you get better power. And that's something you can look at before you run your study. It's something I've looked at. So exercise 2 is, we want to know, it's a pilot study, so there's kind of a fixed sample size already. Last time we tried this, everyone got kind of 60% on both the pretest and the post-test. So they didn't actually learn anything from my practice session last time, but this time I think they will. And I also measured the correlation between the pretest and the post-test. It was 0.7. So, people who did better on the pretest also tended to do better on the post-test. And I think there are going to be 30 students. And I kind of want to see whether this is going to work. So let's see if we have any power. This is a matched paired t-test. And the reason that it's a matched paired t-test, see, it's matched pairs over here. The reason is because we have before and after measurements, and those two things are paired by students, each student's before and each student's after measurement. Oh yeah, okay, I think it's going to improve scores by 20 points. So here we kind of need to determine the effect size based on what I told you. So the mean of group 1, let's make that, doesn't actually, oh, I didn't tell you standard deviations. Oh, you kind of need that, don't you? Well, All right. So I guess I didn't give you complete information now that I think about it, but we can make something up here and go through it that way. So, okay, 60% in group one, and I think they're going to be, 20 points better. So let's give them an 80. And let's say the standard deviation is like, 30 in both groups. Let's just say in the before and after, that the standard deviation will stay the same. And the correlation between the two groups that I did tell you. So I can, and that corresponds to an effect size of 0.86, given all these parameters I put in. And, oh, I forgot. We want to know what the power is, so we have to change this here. This is post hoc. Compute achieved power. So how much power did we achieve? And the total sample size is 30. Right? And we did two-tailed test. Oh, but it set the effect size. That's annoying. Yeah. Now we'll use the effect size we calculated over here. And I'll calculate the power. And it says there's 99% power. Good news. I guess it's a big difference relative to the standard deviation. And 0.86 effect size is pretty big. Anyway, so you couldn't have done that because I didn't tell you the standard deviations unless you made up your own numbers. But that was that. Yeah.
Can you explain why using the correlation between the before and after scores as the effect size would be the wrong thing to plug in to get power? Because that's what I did, and I don't know.
So yeah, that's a good question. The correlation between before and after scores is, okay, so let's say the correlation were 1. Well, okay, let's say everybody got the exact same score on the post-test as they got in the pre-test. Everyone got the exact same score, right? They didn't learn anything, right? The correlation between the pre-test and the post-test would be 1, right? So that's a big effect size for no effect. So they're measuring two different things, really. Correlation is kind of how much information about the post-test is the pre-test telling me. And the effect size is how much does this boost people's scores? I'm sorry? Yeah. Now, if it boosted everyone's score by exactly 10 points, you'd also see a correlation of 1. But now there's a big effect size. A high correlation is really good for power because that means that we can already guess what they would have done anyway, what they would have done without the intervention, just based on their pretest scores, because there's a high correlation. And so if they do better than that, then we say, hey, look, there's an effect, and it's pretty easy to see. But if there's a low correlation, it means the pretest is giving you relatively little value. And we'll see exactly that sort of thing in a couple of minutes as we look at power up. First, I have to remember how to, play from the inside. There we go. All right, power up. Okay, this is the website. Did anyone have trouble downloading Power Up, or did everyone have a chance? So you can kind of go through it with me. Good. I think it's kind of like optimal design. Anyway, this is I didn't know about it. If you actually when you signed up, you saw that I said we were going to talk about optimal design. But then I did some snooping and I found Power Up, which I think is even better. It's really cool. They've got this moderator and meter stuff. I wasn't even aware of it. And they'll let you do stuff for observational studies as well, not just randomized trials. So anyway, it's great. So I don't think they do longitudinal stuff. But one of the big strengths of Power Up, just like optimal design before it, is that it lets you calculate power for multi-level trials. Now, this happens a lot in education. As you see, you have students are nested within teachers, are nested within schools, right? Now, of course, if you transfer from one teacher to another, from one school to another, it messes this up. And you could talk to Tasha Baratfas about this. That's her whole research. That's a part of her research program. But that aside, most of the time you have students nested within teachers nested within schools. So each teacher has a range of different students, and each school has a range of different teachers, and you have to account for that, because students who have one teacher are going to be different on average from students at another teacher, especially if you think about their post tests. Let's say you have a good teacher and a bad teacher, right? And you assign the good teacher to the intervention and the bad teacher to the control. And hey, look, we found an effect. Okay, well, maybe it was just an effect of having the good teacher and the bad teacher. You want to account for that, right? You want to account for the fact that students with one teacher are going to be different from students and another teacher at the post-test. Same thing with schools. You have poor schools and rich schools. You have, magnet schools, and all of that will find itself in the post-test. And, if you randomize one school to treatment and one school to control, and the one school to treatment is, everyone hires, they're rich and they hire, fancy schmancy tutors for all their students. And then at the end, they have much better scores. You say, well, okay, that wasn't because of the treatment. That's because it's a rich school and a poor school, right? It was because of the tutors that all their parents are hiring. So you want to be able to account for all those things. And so you need to account for the fact that different students go to different schools and they have different teachers. And that's all kind of important. Especially if it's the schools that you're randomizing or the teachers that you're randomizing and not the students. That's all called clustering. So at the end, we really, really care about what is being randomized. So there are a few different cases. And you need to kind of understand what all these designs are in order to use PowerUp, as we'll see. That's why I'm talking about all this now. So individual randomization means that I'm just randomizing students. So let's say I go to each student and I flip a coin, and if it's heads, they're in control. If it's heads, they're treatment. If it's tails, they're control, or vice versa. It doesn't matter. I flip a coin for each student. Or, let's say I look at the whole pool of students and I randomly choose half of them for treatment and half of them for control. That's individual randomization. And I'm not thinking about teacher or school or anything. So in that case, you don't actually have to account for teacher and school. You can ignore those. Because within each classroom, you have some people in treatment and some people to control, right? And so you can actually just compare treatment and control students. And, you might have benefit from putting, school and teacher in as like covariates, but you don't have to. So that's individual randomization. Blocked randomization is kind of similar, except it's a little bit more clever. Now, within each classroom, I want to make sure half the students get treatment and half the students get control. I don't want to accidentally wind up in a situation where one classroom everyone got treatment, another classroom everyone got control. Now, I want to make sure that every classroom it's half and half. Or another thing you could do is you take, I'm going to pair these two students because they're pretty similar, and these two students, pairing similar students, and then flipping a coin within each pair. That's another example of blocking. Blocking is kind of, you have a higher aggregate variable like teacher or pair, and then within that categorization, you randomize some people to treatment and some people to control. That's called blocking. And cluster randomizing is now, or sometimes they call it grouped randomization. I'm randomizing the whole classroom to treatment or the whole classroom to control. Everyone in the classroom gets the same thing. Or sometimes I'm randomizing the whole school to treatment or the whole school to control, right? And now the sample size, now when you think about sample size, it's different, right? Does the sample size count as the number of schools and the number of students? Some kind of combination. It has to do with the ICC, which we'll see in a second. So that's cluster randomization, randomizing groups, entire groups of people. Now, by the way, if you do a longitudinal study, so you have several measurements on each person, that's also kind of a clustered randomization because all those measurements you're randomizing all of the measurements within this person to treatment and all the measurements between that person to control. So you can think of all those measurements as clustered within the individual. Right? So there's individual randomization. That's just like flipping a coin for everybody. Blocked randomization, which is like within each bigger group, half people get treatment and half the people get control. And then there's clustered randomization, where it's the entire group gets treatment or control. And you can combine them just to make things more confusing. Now, this is a study I spent a lot of time working on, actually, after the fact. They took schools and they paired the schools together. They said, here are two rich, high-performing schools, let's pair them. Here's two, low-performing schools, let's pair them. And they tried to pair schools as similarly as possible, and then they flipped a coin within each pair of schools, and then the whole school got treatment or the whole school got control. And so it was blocked at the pair level and randomized at the school level. Or sometimes you might randomize teachers within a school. You might say, each school has 4 teachers, and I'm going to randomize 2 of those teachers to treatment and 2 of them to control, but I have several schools. So it's blocked by school and randomized by teacher. And then I measure each student's test score. I need to account for all that in my estimation and also in my power analysis. You might randomize a certain number of schools per district to treatment and control. There are all sorts of combinations of these things. So you kind of in the language of Power Up, they talk about the different levels, and they talk about the different what level randomization is at and what level of blocking is at. So the way it works is level 1, level 2, level 3. The higher the number, the bigger the group. The bigger the hierarchical level. So if you randomize teachers and block within schools, then you'll say that randomization took place at level 2 was randomized, blocked within level 3. Okay, now we can finally talk about ICCs. I keep mentioning them. Now I'm going to actually say what they are. And they actually end up being very important for power analysis if you have a clustered randomized design. So the idea of an ICC is this. Forget school, teacher, everything, forget all the blocking and all the clustered variables, and just take all the test scores or whatever it is you're measuring, all the outcome variables, and look at the variance of those. Now that number, that total variance, can be decomposed into three parts. It's called the log total variation. That can be decomposed into the variance of the school average scores. So like I estimated the average score in each school and took the variance of those averages, right? So if there were 5 schools in the study, there were 5 numbers, and I take the variance of those 5 numbers. That's the school level variance. And then within each school, let's say there are 10 teachers in each school. So now I look at the average scores for those teachers within school 1, the 10 teachers within school 2, 10 teachers within school 3. So now I have the variance of those teachers. So I have the variance of teachers in school 1, the variance of teachers in school 2, variance of teachers in school 3, whatever. I take the average of all those variances, and that's the variance of teachers within school. And then within each teacher, all the students have different scores, right? And they have a variance too. And so what proportion, and the sum of those 3 variances is equal to the total variance. And you can do this actually. It's exactly equal. This is arithmetic, the law of total variation, or law of total variance, right? Some proportion of all of the variance is at the school level, and another proportion of the variance is at the teacher level, and another proportion of the variance is at the school level. Another way to think about it is, why are two people's scores different from each other? Part of it is because they went to different schools. Another part of it is because they have different teachers. Another part of it is because they're just different people, right? And this kind of tells you which, obviously with two specific people, you can't really ask, answer these questions that way. But on average, this tells you what proportion of the difference between two people is attributable to each level of the hierarchy. And that's what the ICC is. The ICC is what proportion of the total variance is at the school level, and what proportion of the total variance is at the teacher level within schools. And, well, whatever's left is at the student level. So there are actually two ICCs, because the third one is just one minus the other two, right? Because it all has to add up to 100%, or it all has to add up to 1. So some proportion of the variance is at the school teacher level, and some proportion of the variance is at the school level. Now, for a clustered design, the smaller these two ICCs are and the bigger this one is, the better you are. Because if students at two different schools are the same, then it doesn't really matter that you randomized at the school level or the student level. But if they're very different from each other, then that means that the school explains a lot of the variance, and then it really matters that you randomized at the school level and not the student level. But okay, anyway, we'll get to that maybe a little later. Okay, there are other parameters that it's going to ask you, that PowerUp asks you about, other than the ICC. One of them is the R-squared. This is kind of what we were talking about before. This is like the correlation between the pretest and the post-test. So I didn't just measure people's outcomes and what treatment group they were in. I also measured, other variables. Are they English language learners? Are they get free reduced price lunch? Whatever. And I have a whole, and maybe I measured their pretest. I have a pretest score, right? I have a whole thing. And all those things are might help me predict their outcomes. And the better I can predict people's outcomes based on their covariates, based on these other variables, the more precisely I can estimate a treatment effect, right? Because let's say, imagine that I had a vector of covariates that would tell me exactly what their post-test would be if they were in the control condition, right? Let's say 100%, I could tell you exactly what your post-test is in the control condition. And then if you're in the treatment condition, I know exactly what the treatment effect was, right? It's whatever you got minus whatever you would have gotten in the control condition. So high R-squared is good. You want your covariates to predict the outcome. And then, you want to know how many teachers within schools and the total sample size, things like that. Then there's this whole rigmarole about whether you have constant or fixed or random effects, and it's late. And wow, we're already 9 minutes over, so I'm going to skip this. And I can show you a little bit about all around. If you need to leave, I'm not offended, but if you want to stick around, you're welcome to. And it's all going to get recorded, so you can watch the rest of it here. So when you open up the spreadsheet, or whatever, the Excel sheet, this is what you see. And if you're very clever, you can just choose whichever design you want this way. But if you're like me, then you start here and you step through the process. And they ask you, what kind of study design? I told you about these three. These are like observational studies, which we're not going to get to because we're already past time. Individual random assignment is like a coin flip for everyone. Simple cluster random assignment is I randomized school or I randomized teachers or something like that, but there was no blocking. And blocked random assignment is, well, there's blocking. And this includes blocked clusters, right? And you can always click start over and it brings you back to the beginning. But, let's say you have 3 levels, or let's say, we were talking about 4 levels. So let's say you have pairs of schools, and then you flip a coin within each pair, and then one school gets treatment and the other school gets control. And then you have like teachers and you have students. So, so what level is the treatment delivered at? So like who got randomized? Did the schools did level 2 get randomized? You have 4 levels. Did level 2 get randomized? Did level 3 get randomized? So if it's schools that got randomized within pairs, that's level 3, right? Because you have students, level 1, teacher, level 2, schools, level 3, pairs, level 4, right? School pairs, level 4. So level 3 got randomized. Now they give you this option. Actually, so this is a mistake. This should say random effects here. I don't know if it says fixed effects for y'all, but they made a mistake. I should email them probably. That's why there's an R, because it stands for random. But it doesn't. You can put in school level covariates here, or you can put in pair level covariates. I mean, if you have random effects, you have fixed effects, you can't. But then you have to whatever. Anyway, just do fixed effects. It's easier. And then you can either there are only 2 possibilities here. You can look at the minimum detectable effect size or the sample size. I think, did I mess myself up? Okay, no. So let's say I want a sample size, and then I have to put in all my parameters here. I don't know. It always puts it down to 80%. Maybe you can see it better now. And it doesn't do the nice thing that GPower does, where you can put in the raw values and it spits out the effect size for you. You have to actually like calculate the effect size yourself, or choose an effect size that you like. But a lot of the same stuff. Here it's got 80% power and 2-tailed test. Those are the standard things. The yellow things you can change. Light yellow is like standard, but you can change it if you want to. Normal yellow is something you can change. So there are a lot of things you can mess with here. This is the effect size. This is like Cohen's d. That's the thing we care about, the Cohen's d effect size. So, and then here are the 2 ICCs, because the proportion. The proportion of the variance at like the school level and the proportion of the variance at the teacher level. Now the question is, so now we're randomizing schools to treatment or control. Is it half to treatment, half to control? It doesn't have to be. It could be something else. So I could put in a different number here. This is like the allocation ratio, right? The proportion of people of level 3 units, schools in this case, that are randomized to one or the other. And now we have 3 different R-squared values, because you might have covariates that have to do with the school, and you might have other covariates that have to do with the students, and other covariates that have to do with the teachers. You'll have all sorts of covariates. And so each set of covariates has its own R-squared. How well does that predict the school? How well does that predict the teacher? How well does that predict the student? Right? And then the number of level 3 covariates you want to put in. I don't know why they don't ask you about the number of level 2 or level 1 covariates. And I'm sure there's some reason, but whatever, I guess that's not relevant. Or this is the most relevant of all of them. And now they want to know, okay, how many students are there in a class? How many level 1 units are there within level 2, in each level 2 unit, right? And how many level 2 units are there within each level 3 unit? So how many teachers are there within school? I mentioned, they say, we want you to use the harmonic mean. I put up the equation for a harmonic mean, but whatever, you can use a normal mean, it's probably the same thing. And then, okay. And now we want to know how many, so if I have schools in pairs, then there are 2 schools in every level 4 unit. The pair is level 4, the school is level 3. So this number would be 2. If I have districts, if I'm randomizing schools within districts, now how many schools are there within every district? Now you have to average over all the districts, and they want you to do the harmonic mean, whatever. But how many schools per district? Or how many schools per pair, or whatever it is. And now you put all these things in, and you click run, and it fills in the number in the green. 10. So that means you need 10 pairs, 10, or here there are 4, so 10 quadruples, right? 10 districts or whatever it is, 10 level 4 units. And we can go back and then start over and we can try it again with another thing. Individual random assignment, you'll see, is much simpler. Okay, now, all we need is, we need these three things, which are standard. The effect size, which is always going to be something. And then in the allocation, how many are randomized to each thing. And then all it's asking for is an R squared. So, and the number of covariates. And if you don't have any covariates, you just set this to 0, and 0. And then, you'll see it. It'll tell us we need more people now. A lot more people. So having covariates helps you a lot, actually. So there's all sorts of options here. If I'm just randomizing teachers, and I want to figure out the sample size, here's my effect size, and fill all these things out. There's only one RCC here because it's only 2 levels. What proportion is at the teacher level, and the rest is at the student level? There's no schools, right? In this example. Oh yeah, look at that. It lets you, if you have attrition. So some people drop out of the study. It lets you account for that too. Interesting. Okay, and then how many are allocated to each sample, et cetera, et cetera. There's all sorts of things you could do. It's pretty neat. So let's go back to, okay, now this is what I would use for the bilingual study. And this is what I used, right? I wanted to know what effect size we could see with the study as we had planned it already, because there's a pilot study. So these things I left at the standard numbers. Now I picked out these numbers from that paper, Hedges and Hedberg. Although I think I modified them a little bit because I don't know. It was a long time ago. Half and half to treatment and control. Okay, but by the way, this is the 3-level cluster randomized assignment because it was the schools randomized, and there was no blocking. It was just 10 schools, 5 in each. There's no blocking in this case. We thought there were 30 students in each class and 8 teachers, or 30 students for each teacher and 8 teachers in each school. And there were a total of 10 schools. And then it said I could find an effect of 0.5. That's it, effect size of 0.5, we'd be able to see. Okay, I have some exercises here. If y'all want to try them. And then just a couple of slides about Monte Carlo. You guys want to try the exercises? Or should we just go through them together? Let's just do that. Yeah, it's late. Okay. Sharina. Oh, no. I wanted to do the opposite. Okay, so we have an RCT, 100 students nested within 10 teachers, and we're randomizing the students. And okay, so half students randomized to each condition. And I think I meant half students in each teacher are randomized to each condition. And then there's kind of an ICC of 0.3 here. So 30% of the variance in student scores is explained by the teacher. There's no covariates. And I want to know what effect I could see. What's the minimum effect I could see in this design? I said use a fixed effects design. So this is a, what do we think this is?
Individual randoms.
It could be, yeah, but it's actually blocked because I didn't specify that. I said it, but it's not written down there. But yeah, because within each teacher, half are counted, so it's blocked. So say blocked. How many levels? Yeah, 2 levels. Teacher, student, 2 levels. And I said use fixed effects. And then which one of these do we want?
MDS.
Yeah. Yeah, because we already know the sample size and we want to know what effect size. Okay, so let's plug in numbers here. So, okay, half and half randomized to each group, so we'll leave that as it is. And there are no covariates, so we'll set this to 0, right? And this will also go to 0. In each student, in each teacher, on average, there's 10 students, because there's 100 students nested within 10 teachers. I didn't use the harmonic mean like they tell you to use, but I'm a little bit of a rebel. So, and then number of blocks. Remember, the blocks are the teachers, right? Because the students are nested within the teachers. Right. 10 blocks. And then this stuff they calculate for you. And now what's the minimum effect size? I have to find where it says run. Let's start over. Wait, doesn't it tell you? Am I missing something here?
Press enter. It changes automatically.
It changes automatically?
So that it's accept. So it's calculating.
Oh, yeah.
What the function is.
Look at that. Yeah. Changes automatically. All right. So it says I could detect an effect of 0.56 or 0.57. Good. All right, that was exercise 1. So let's start over. And okay, exercise 2. I'll do the step-through process again. So it's the same thing, actually. We have 100 students nested within 10 teachers, but now instead of randomizing students within classrooms, we're randomizing the teachers themselves. So we'll have, and half teachers teach, so 5 teachers to treatment, 5 teachers to control. So what's this? Simple cluster, right? Because it's the teachers are clusters, and they're being randomized, and they're not blocked in any way. I'm not talking about like teachers within schools here, just teachers. They're all in the same school or whatever, right? So it's blocked random assignment. Okay.
Blocked.
Oh no, I'm sorry. You're right. Yeah, simple cluster. Sorry. Yeah, I was testing you. Simple cluster. Okay. How many levels? 2, right? And I think, yeah, we're looking for the MDES as before. Okay. So now we can plug in the same things. What's the ICC? Except 30%, which is 0.3, right? And then what goes here? Proportion. Yeah, 0.5, so leave that as it is. Okay. How about in these two? There's no covariates. Oh, sorry, here, let me. This is the R squared, so proportion of level 1 covariate outcomes, variance explained by covariates. Yeah, so there's none, so set these to 0. And then the number of covariates is 0. Okay, and okay, how many level 1 units within level 2 cluster?
10.
Yeah, 10. The number of level 2 units?
10.
Yeah, 10. All right. And so the minimum detectable effect size is 1.2, 1.23. Much, much bigger, right? This is a much less powerful design. So I thought, the same data, it's just a different design. All we changed was the design, right? But by randomizing at the cluster level instead of at the student level, you lose a lot of power. Sometimes you want to, there are good reasons to randomize at the cluster level. For instance, if it's like teacher training, you can't do that at the student level, right? You have to do it at the teacher level or higher, or something happens, curriculum or whatever. It has to be at a higher level. So there's a lot of practical reasons. Another thing is, if you have randomizing something at the student level, sometimes the students talk to each other, and then you get like spillover effects. and you might want to avoid that. So there's all good reasons to do clustered randomized designs, but you lose a lot of power when you do that. So that's just good to know. All right, let me just say a tiny bit about Monte Carlo studies. I showed you one already. I wanted to put this up in case, you know, it happens that this is what's necessary in your research study, and you want to come to me or to Young-Ree and say, you know, let's do a simulation study. And now you kind of know what we're talking about. If, you know, if Young-Ree says, I think we need to use a simulation study for power, then you'll say, oh yes, I remember that. I came to the workshop. So, we saw an example of this already. You make up a data generating model, based on what you think the reality is. You know, you set the numbers. You know, I have these covariates. This is the effect I think the covariates have, and I'm going to estimate. And you know, you can put in ICCs, all R squared, all these values you stick into your data generating model, and then you simulate fake data based on all of those numbers. And then you do your analysis. You do your statistical analysis on each of the fake data sets. And you count how many times you get a significant effect. That's all it is. So it's very simple in theory, but in practice, it actually ends up being, you know, takes a lot of time because you have to code all that stuff in. But, you know, they've already done the work for you. It also, you have to wait for the computer to run through all the, you know, all the things where here they're using a formula, so it's basically instant. Yeah, it's nice with Monte Carlo. You can do anything, like literally anything. You know, and anything that you could run a statistical analysis on, you could do a Monte Carlo study to estimate the power. Might take a long time, but you could do it. You know, if you don't think your data is normally distributed, all the stuff, you know, all the power up stuff assumes normally distributed outcomes, right? This doesn't, you know, whatever it is you want to do. And, you know, the more kind of advanced the statistics are often, the more you have to kind of really think through what your assumptions are. And that's, it's annoying, but it's also nice about Monte Carlo is that you have to, it forces you to really think about like, what are all the parameters and what do they mean, you know, rather than just like plugging in numbers. So that's kind of nice too, I think. And it might be more accurate because it's actually like simulating the thing that you're doing instead of using theory. But on the other hand, it's much more work, and you have to be able to code in order to do it, right? The last thing I'll say about it is that like it's much more likely for you to make a mistake in running a simulation, right? There are bugs. You code a bug, and then you end up. This happened to me once. It was very embarrassing. But you know, I told someone their study was very, very well powered, and then I realized it was a mistake in what I was coding, and I had to tell him that no, actually, his power was much worse. So that was like when I first started here. I've gotten better at it since then. But you know, that doesn't happen with optimal, with you know, power up or G power. You know, you see what numbers you plug in, and you see the outcome you get, and there's not as much room for mistakes. So that's the thing. Okay. Anyway, power analysis is great. You know, I hope that y'all at least feel like you can maybe use power up or G power to power your own studies in some scenarios, and in other scenarios, you know what you'll need to know or what's going to happen if you come to talk to me and Young-Ree and ask us to do power analysis. You know what we're talking about, I hope. And you know, if you're interested, there's plenty of web resources to figure out how to do your own simulations or use one of the other programs or something like that. You know, but